Good morning, students. This is again back to discuss a very important question in electromagnetic induction in that time varying field. Okay. This is again a critical question. So be very careful here. These are my credentials. Okay. So the question is, a uniform time varying magnetic field exists in a cylindrical region. Okay. A non-conducting charged body is placed inside it with a fixed axis of rotation coinciding with the axis of cylindrical region. This is cylindrical region B existing here, and this is a body. As you see, this is an arbitrary shaped body placed such that is an axis of rotation which is coinciding with the axis of the cylindrical region. Call it OZ. Okay. This is XY plane. Let's say this plane is XY plane. OZ is the axis of rotation. It is also axis of the cylindrical region. Okay. That's what written. OZ is the axis of cylindrical region and also the fixed axis of rotation of the arbitrarily shaped body. This arbitrarily shaped body, as I did this shaded one. Okay. So now the magnetic field B is suddenly switched off. What will be the angular velocity? You might have done this type of questions, but I'm making it a bit more generalized. Okay. If B is uniform, and is time varying, non-conservative electric field appears in closed circular loops. This one such closed loop electric field I am showing. If the B changes, the uniform B, which is if it changes, even if it's not uniform B also, even if it is symmetric about the axis, may not be uniform over the area, but must be symmetric about the axis, then also the closed loop electric fields will appear. And uniform field is a special case of symmetric field. Okay, so the closed loop electric field, as I given you the direction, because this is decreasing suddenly. So that means the field which is pointing into this suddenly decreasing. So decreasing means it is as per the Lenz's law, the ENC will appear in a clockwise manner. ENC will appear in clockwise manner. So this I'll write it as ENC. ENC means non-conservative. Remember this. When I say NC, it is non-conservative. So non-conservative electric field appears in closed circular loop. So to make it clear here, I write it as ENC. Okay. So I told you to see the red circle in the figure. This is the red circle. This is just one of the electric field lines. Graphically, I have shown the circular loop clockwise manner because field B pointing into the plane and suddenly switched on means decreasing. Case 1, this radius measured from the axis, that is small r, is less than capital R. You must be knowing ENC is R by 2 dV by dt. You must have studied it earlier. In my previous lecture, I have discussed this. So B is the uniform B. That's why I wrote dB by dt. Otherwise, I would have written B average by dt. dB average by dt if B is not uniform but symmetric. In these two cases only, I can calculate the ENC. In the cylindrical region, B should be uniform or should be symmetric about the axis and should be changing with time, maintaining the symmetry. Then only I can calculate the ENC in this space. Otherwise, in other geometry, is not possible. Then torque is how much? Due to that, you take a dq element. So the force will be ENC into dq, clockwise manner, and into small r will be r dq into ENC will be the torque component along OZ. Okay, so that is r square by 2 dq into dv by dt. This ENC I wrote here. So torque OZ is the integration of this r square by half dv by dt into r square dq. I have to integrate. This is torque OZ, is the component of torque along OZ. So that is nothing but you must be knowing from the basics of rotational mechanics, that is the torque OZ is d by dt of LOZ. L is the angular momentum of the component along OZ. So half dv by dt r square dq integration, that is torque OZ, that is also dLOZ by dt. Yes or no? So I can write here the torque OZ is equal to this. Now it will be clear to you. I'm just writing this scalar part of it, even if we derive it vectorially. Okay. So now you see dt 5 cancel. So dLOZ is equal to half this r square dq integration into dv. Integrating both sides, I'll get delta LOZ is half r square dq into delta v. So LOZ initially it is 0 because there is no angular momentum, it is rest. The disk is at rest. B is equal to some b. So LOZ will be half r square dq integration into b. This is the angular momentum of the disk once the field is switched off. Okay. Okay. So I'll write here, finally, after switching off, LOZ is some LOZ, B is equal to 0. Right? So LOZ 0 to LOZ, the delta L is LOZ, and B becomes B to 0, so change is B only. So this LOZ half r square dq into B. Right. So LOZ is a fixed axis rotation, that is IOZ into omega. So half r square dq integration into B. So r square dm integration omega. What is IOZ? Nothing but r square into dm integration. You must be knowing from the basics of rotation. Yes or no? What is I? Moment of inertia about OZ, that is perpendicular distance square into dm integration, r square dm integration into omega is half r square dq integration into. So what is omega then? Half r square dq integration divided by r square dm integration into B. Yes or no? Is it okay? So what is r square dm integration? As you know, that is mass into radius of gyration square. Radius of gyration about the axis of rotation. That is, call it Km. But similarly, same argument I can make for the charge distribution also. R square dq I can write q in total charge into kq square. Kq is the counterpart of Km. Km is radius of gyration about OZ axis, but kq is the counterpart of radius of gyration of charge distribution geometry about OZ axis. If charge is distributed a particular geometry, then r square dq integration will be total charge into kq square. Kq is the radius of gyration counterpart. Okay, so that's a very, just imagine that the charge distribution is something like a mass distribution. So whatever the radius of gyration, that is the kq. Okay, so that's what I wrote. If the geometry of charge and mass distribution same, then kq and k will be same. Yes or no? That's what I wrote. So let the good example at the Raume. Let the body be uniform disk of mass m and radius r, and also uniformly charged. So mass distribution, charge distribution both are identical. In that case, km square, kq square will be r square by 2. So omega will be, just use this equation, q by, this is km kq equal, so cancel, so qb by 2m. That's it. From equation 5, it is qb by 2m. If the charge q distributed only on the circumference of the disk, then what will happen? So km square is r square by 2, but kq square is a ring type of geometry, so kq square will be r square. Is a ring geometry as per charge distribution concern. So kq square is r square. So r square dq integration with total charge q into r square. This one basics of rotational dynamics. So qb by omega is qb by equation number 5. Omega is qb by 2m. Kq square by km square. This is r square by 2. So 2 cancel. So qb by m. Okay, so the very simple one. Don't derive it from the first principle of all the cases. This thus is simple case. As long as B is uniform and the whole thing is inside the magnetic field cylindrical region, then you can use this. This is the omega half q by m b into kq square by km square. Okay. और एक एग्जांपल लेते हैं. Instead of a disk, make uniform equilateral triangular plate is placed inside the magnetic field. The magnetic field above, so whatever magnetic field I have shown in the above diagram, same magnetic field, make equilateral triangular plate is uniform. Equilateral triangular plate is placed with its axis of rotation passing through the centroid and matching with the axis of cylindrical region. बस cylindrical region जो axis है उसके साथ उसका भी जो axis passing through centroid is matching. Now the charge q is uniform distributed only on its sides. उसके side के ऊपर ही charge distribution है, जबकि mass is throughout the area. So find the angular velocity of the triangle when the magnetic field is switched off. So km क्या होगा? Is a triangular plate. Uniform triangular plate km, you must be knowing from the basics of rotation. Ioz by m, ms square by 12 by m, that is a square by 12. Q is only on the sides, remember, not inside. So Ioz will be ms square by 6 by m. You tell how do you do this? This is from the basics of our moment of inertia topic covered in the rotational dynamics. If I have a equilateral triangle, the 3 rods forming equilateral triangle, and rods are uniform mass density. Each of rod mass is the total mass is m. So then you can calculate the what is the moment of inertia of that about the axis passing through the centroid and perpendicular to plane of the triangle. Okay, that will be ms square by 6 divided by m square by 6 is the kq. Now apply the equation number 5. Very simple. This is not discussed in your books, but this will make things very simple. qb by 2m into kq square by km square. Thus that I am using qb by 2m kq square by km square. kq square is r square, km square is r square by 2. So 2 goes off, so 2 cancels. So this becomes qb by m. Okay. Suppose the charge would have been distributed uniformly throughout the surface of the triangle, then qm, kq and km would have been same. So is the omega would have been qb by 2m. Sorry, here a square by 6, a square by 12, so it becomes 12 goes up, so become 2 cancel, qb by m. Okay, if the mass and charge distribution would have been identical, that means charge would have been distributed uniformly throughout the area of the triangle, then it would have been qb by 2m because kq's and km would have been same. So this would have been the omega. That's what I wrote. Now for the case 2, if r is greater than r, let's go to the next page for that. then mass and charge is distributed outside this. Sorry, the charge is distributed outside this. So let us go. Let us go to the second page. तो सेकंड पेज में जाएंगे हम लोग. अभी हम लोग देख लेंगे उसको सेकंड पेज में. ये आ गया सेकंड पेज. केस 2, R greater than R. Then what is ENC? You must be knowing already. Capital R square by 2R dV by dt. Capital R is the radius of this cylindrical region. Must be knowing this. So, and B is the uniform B, changing with time. So d tau will be how much? dq ENC, just like what I did in the past case. dq, small element charge dq into ENC into R. So R cancels here. Are you observing this? So the torque seems to be constant. It doesn't depend upon small r anymore. So total torque will be simply r square by 2 dv by dt into dq integration only. It was earlier r square dq. Now it's only dq. So that becomes capital Q. So this is a much simpler expression for the outside of the cylindrical region. So then by this whatever I discussed in the case 1, similarly dl oz by dt is torque oz is equal to r square by 2 dv by dt into q. dt cancel. So delta lz is this. So integrating, l oz will be equal to r square by 2 q into b, because these are the delta b is b only, delta l will be l oz. So omega will be, if it is a fixed axis rotation, then omega will be q r square b by 2 I oz. But I oz I can write as m km square. That's it. This is a very important expression. So torque doesn't depend on the value of small r when r is greater than capital R. So एग्जाम्पल लेंगे. ये इसी को आपको याद करो. Here kq square है, but इस kq square के कुछ नहीं. It is simply it is r square. But km square there is as before in the denominator. So in the uniform disk of mass m and radius 2r now has a charge q uniform distributed on the circumference. Circumference में ही distribute है charge. That means since it's 2r, so it is outside the cylindrical region whose radius is r. It's placed coaxially on a cylindrical magnetic field region of radius r, but this disk radius is 2r. Having uniform magnetic field B and magnetic field is suddenly switched off. Find the angular velocity. But कोई problem नहीं. OZ is axis of rotation. Charge q is outside. So IOZ will be, what is IOZ? Half m into 2r whole square. That is 2mr square. That is m km square. That is km square is 2r square. है ना? M km square is the IOZ. M km square is m into 2r square. So km square is 2r square. Applying equation 9. जो equation 9 हमने लिखा है ओमेगा, straight away apply कर दो. Omega is qb r square by 2m km square. So qb r square by 2m into 2r square. Km square is 2r square. So qb by 4m. But simple answer. Okay, in all the above cases, like page 1, page 2, all the cases say this angular momentum stored in the electromagnetic field gets transferred to the disk or the rotating body. That's it. Am I clear? As I discussed this in the previous topic, as you must be knowing, you can see my video lecture on the paradox in electromagnetism. That's where I discussed the momentum stored in the electromagnetic field gets transferred to the disk if this field is switched off. And this conforms to the conservation of angular momentum. Okay, right? All of you clear? This is the second part of my discussion. Then third part will be a very generalized one. I think all of you have discussed, all of you have understood this. I'll be very happy if you get benefit out of it. And many exams they are asking if the charge is distributed on the sides and it is a solid triangle. All this you can do. Just see if it is inside the magnetic field, you can see this. Just our page 1. simply we can use our basic expression here. Very nice expression. Q by n, kq square by km square into b into half. That is the omega. With inside this. Mostly they ask this inside only, but they can ask outside also. And next class I'll be discussing the B is not uniform but symmetric about the axis of the cylindrical region, and the body may remain inside as well as outside. Okay, so this next one will be a bit more involved discussion, but still I'll do it for you. You go through my notes as well as you listen to my lecture, go through my notes, and if you have not yet subscribed, you subscribe to my channel. I'll coming regularly with more and more conceptual updates in physics, various topics. So thank you all. We'll stop here. We'll meet very soon with the next topic in the series. This is a topic in, I think this is part 2, critical topic, part 2. Okay, we'll come with part 3, which will be more critical. But for that you have to understand this, and if you want to understand this, you also, if I miss the part 1, read that part 1 also, refer to part 1 also. So thank you all. All the best to you. Have a good day. We'll meet soon.